Okay, so welcome everyone to lecture number 9. So in the previous lecture, we have learned how to simulate damping oscillator system. So what damping oscillator system is? So inherently it is a nonlinear oscillator system. So I mean you have a differential equation of second order. So x double dot plus gamma x dot omega square x, and here you have a nonlinear. So this is the nonlinear term, and you can have your tribe also. So okay, so this is the nonlinear term. So inherently this is a nonlinear oscillator. Now when your system has nonlinearity, so there is a very special phenomena which I mean for a certain range of parameter value you can observe, and that is chaos. So in today's lecture, so I will show you. So I will not go too much deep into the chaos theory, but I will briefly discuss first. So briefly discuss what chaos is. Then I will talk mainly in this lecture. I will talk about how you can calculate Lyapunov exponent. Calculate Lyapunov exponent. And what is this Lyapunov exponent? So it is the mathematical. I mean, it is a quantity, mathematical quantity. I mean, you will not gain any extra physical information for every system from Lyapunov exponent. But this is a mathematical quantity, and if you can, I mean, for a certain value of this quantity, if you can, I mean, if it is greater than 0, then you can surely tell that your system goes into chaotic region. So in this lecture, we will I will mainly discuss about these two things. So mainly it will be focused on how to calculate Lyapunov exponent, and also first I will discuss how chaos is. Okay, so I mean, what is chaos? So chaos is nothing but I mean, so basically divergence in a system. I mean, you can think of it as unpredictability. So suppose I mean you have a system. I mean you have very two uh, close by initial conditions. So suppose I mean you have an equation and you start with two points which are very close by separated. So this is the initial point, and you want to track the distance between these 2 points. So what is the distance between these 2 points after a certain time? So for example, so it will have its own time evolution. So I mean, if we think this as displacement, so this x will have its time evolution, and I mean you are starting from a very so if this is x0 and this is suppose x0 plus delta, and this x0 delta, so it will also evolve according to the time. So I mean, so there is a governing equation of this evolution. So dx dt, for example, consider, suppose the governing equation is like general equation dx dt equal to function of xt, and according to the rule your system is evolving, and you want to track what is the separation between, so this x0, this is the initial point, and this another initial point x0 plus delta. So your separation is delta, and with time, so each of the point, so this initial point you can put here, you will put the initial condition here, and according to the update rule it will evolve. So and similarly this if we put this initial condition, then according to the update rule, this trajectory will also evolve. So this separation delta, so that is I mean evolving as a function of time. So delta evolving as a function of time. So I mean, suppose this is delta initial. So let us call this delta 0. So delta is a function of time, and delta at t equal to 0, it is delta 0. So this is my initial condition. Now I want to know how delta t depend on delta 0. So if I mean the system, I mean so now for what should happen? Ideally, I mean for most of the system, so if we consider two nearly separate initial condition, so this delta t will with time for finite amount after large enough time, so it will remain delta 0 or it can converge. I mean so it may go to a I mean equilibrium point, so it may be minus lambda t or something, so it can converge. Now it may happen for system for certain system that this I mean instead of convergence, so there is exponential growth of this nearby separation. So I mean we are starting from two different initial condition, and with time I mean the system look completely different. So I mean you cannot predict. So I mean so what is the implication of this? So for example, you consider an initial condition, and with that condition, after a certain time, you know that this is the condition of the system right now. This is the state of the system now. So if I mean now what you will do, so generally if you want to predict what your system will behave, so you will consider another nearby point, and you will assume that it I mean it will I mean this distance will not change over time, or it may exponentially convert. So you will consider this or this. I mean around this, its final state will be. So you will state. I mean you will tell that after this time. So if this is the initial condition, then system will come here or around here. But what happens is if there is chaos, so instead of finishing very close by, so it will I mean it can grow exponentially rapidly, and you cannot predict by just looking at the initial condition. And I mean so for example, I mean if there is a very slight change in initial condition, the system becomes unpredictable. You cannot predict what is the future of the system. But the underlying governing equation, but the beauty is underlying governing equation is still deterministic. So I mean you don't have any noise present in your system. You have a deterministic an ordinary differential equation, and you are considering, but there exists a parameter range for which your system behave completely. You cannot predict the system state. So so that is the I mean difference between chaotic behavior and noise or randomness. So in case of noise, so you I mean your system is not an ordinary differential equation. I mean you cannot describe it with ordinary differential equation. So there is but in case of chaos, what is happening? I mean you have your system which is governed by an ordinary differential equation, and it is still deterministic. But uh, for certain for very depending on the nature of the system, and for in the for certain range of parameter value, your system will go into a certain state where you cannot predict what the system of the you cannot predict the future. And what is why can you see this kind of behaviors? In weather system. So in weather system, if we have, so weather system is chaotic system. So that's why we cannot predict what the weather after 100 days. So we right now, even with the finest technology available, we cannot tell what will be the temperature after 10 days at 3 p.m. So that we cannot, that we never can never tell, because whenever we dealing with simulation and whatever it is. So there is I mean if if the system is chaotic, so very slightly different changes in initial conditions. So for example, you put your number to be this in a simulation, but it may happen that your actual number is this. So this slight change, so this can lead to a very large change if there is chaotic behavior in a system. So that's why in weather system, in financing, so in stock market and so on. So that's why you cannot predict. So these systems are inherently chaotic. So and now so this system is inherently chaotic, so you cannot predict what the state of the system will be. Okay, so now so we are talking about distance. So distance in two close by separated point. Now so this is understandable for 1D systems. We have one. So for example, this is variation of displacement with time. So let us take. But if you have a higher dimensional system, so for example, we have nth order differential equation dnx dtn. So for example, we have this nth order equation. So there will be have x, t, and so on. So in that case, how we will calculate the distance? So there, you have to calculate the distance between state vector. So for any kind of system, you for to observe if there's to look in principle look if there is any chaotic behavior or not. You have to look at the separation of the state vector. So what is a state vector? So you have to look at the separation in the phase space. So why in phase space it is needed. So so for example you have a second order harmonic oscillator. For example this is plus omega square x 0. So here so for chaotic system what you will check. So so you can think of you have to check the separation between x at t and x1 t1 x2 t2. So this is after a finite long time and this is your initial condition. This is your initial condition and this is a very closely separated point which is let us assume del x10 plus delta 0. So there delta is the separation. So but if you are dealing with this in harmonic oscillator, so to describe the state of the system, so you have to know two variables. One is the displacement, and you also have to know about velocity also. So by knowing only one parameter, you cannot de describe what is the state of the system. So you can think of it. So let me give you a real world example. So suppose you are in a dense forest, and so you want to go. So for example, you have a dense forest, and so here you are standing in a forest. So there is a so for example there is a, let us say, an mountain. So it is not look like mountains. Okay, so mountain, and suppose here you have river. So and suppose you don't have any idea about this mountain. So so you don't have any idea about this height axis, and you want to uh, go to a point which is so suppose you want to go to this point. So if you don't have any idea about height axis, then for this, and so for example for this point, and there also you don't have any idea but there is a height axis. So there will be also another point. So for example this is x a y a and z is 0, and for this point let us say its value is x a y x a y a z. So this x value and y value for this point and x value y value for this point are same, but this is z0 and this is z equal to z. Now so so if you don't have any idea of the z axis, so these 2 points will seem almost identical to you. So if you look on a 2D map, So I mean you have a map of the so for example you have a map of the of the jungle which is 2D. So in that map there is no mention about height axis. So I mean you what will happen? So I mean you know what is the xa and ya coordinated, but uh, since it doesn't have any information about the z axis, so I mean if you take a wrong turn anywhere, so you may end up being there. So according to map, you are still on this XAY point. So this 2D map says that you are on the right point, but actually you are not. So you are a very far distance away. So that is why. So that is why to I mean to specify the state of any point here, you need the z coordinate also. But if you don't consider the z coordinate, so while I mean looking at the 2D map which doesn't have the z coordinate, so these 2 points will be seem very close. I mean they will seem identical to you, but actually in reality they are not, and they are very far separated. So that is why I mean when you are dealing with the system, you have to calculate the separation between the state vectors. So I mean, and what the state vector will compose of? So in that case, state vector will have three coordinates. So it will have x coordinate, y coordinate, and z coordinate, and you will have to look at the separation. So I mean, if this is x, so you have to look how this state vector is evolving in I mean in the phase space. So that's why to compute. Okay, so to know, we have to look at the evolution of state vectors with time, and have to see if there is any exponential divergence in closely separated nearby trajectories in phase space. So we are looking at the divergence of nearby trajectories in the phase space. So effectively we are looking at the evolution of the state vector. So that is why I mean when you are dealing with this harmonic oscillator equation, so you have to look at the evolution of both x and v. So this is your state vector. So let us call it x, and we have to look at, so I mean we will have some initial condition, and so this is I mean our x0. Then we have to look at how I mean xt and x0 changes. So I mean we have these are initial condition, and we will have I mean very closely separated another point. Then it will evolve like this, and it will go to something like this. So delta t. So we have to look at how this delta t is changing in this x I mean in this xv dimensional in this xv phase space. So here the I mean the dimension I mean the space we are using is the I mean the space of the state vector. So you have to keep that in mind. So now how so now to know I mean so mathematically how we can do this. So mathematically the way is to calculate the Lyapunov exponent, and it is the primary indicator in any system. So basically how it is defined. So so it indicates how fast nearby trajectories in phase space either, so it can either converge or diverge. So if you want to speak it, speak in quantitatively. So quantitatively, so it is the mean exponential rate of convergence. So or divergence. So it is the mean exponential rate of convergence or divergence. And so when this Lyapunov exponent, so this is positive, it is greater than 0, so it indicates chaos. And when we have this Lyapunov exponent less than 0, so it basically indicates stability. So there is system, there is no, for that parameter value, so there is no chaos in the system. Or it converges to fixed point, so there exists fixed point in the system. Or so there can be limit cycle and so on. So you, in the nonlinear dynamics literature you will find it. But the idea is to show if there is chaos in a system, so there has to be Lyapunov exponent. And and it is also quite, so to observe this chaos in a system, so there has to be some non-linearity present in the system. So now let us look at how we can compute this. So let us proceed step by step. So step to compute. Now, how many Lyapunov exponent you will get? So let me mention you, it that. So so number of Lyapunov exponent will be equal to the number of dimension of phase space. So if you are having a three-dimensional, if you need three-state vector to define a system, so there will be three Lyapunov exponent. So we'll shortly we will see why it is, and we have to look at the largest Lyapunov one. So to know if there is chaos in the system. So if there is at least one Lyapunov exponent which is greater than 0, so your system, uh, uh, there is chaos in a system. So and if there is two Lyapunov exponent which is greater than 0, so that is the case of hypochaos as you can, yeah. So but the idea is that to be exist chaos, there should be at least one Lyapunov exponent which must be greater than 0. So let me show you steps to compute it. Okay, so suppose you have a multi-dimensional system. So we any higher dimensional system we can write in this way. So if we have, because any nth order system we can decompose it into n first order system, and if we are decompose it into n first order system, so any nth order ODE can be decomposed into n number of first order ODEs. So what will be x look like here? So x here is this, so x1. So let me write down this as a column vector and xn. So since there is This is a nth order system, so we can decompose it into n first order ODEs, and this is how a state vector will look like. Now suppose we have 2 points. So suppose one is this xt at time t, and another one is xt plus zt. So this is these are the 2 points which are very closely separate. So closely means so very close by say trajectories and initially. So initially, I mean, we start. So suppose we have a system like this. I mean, this is our differentially. This is our system governing. I mean, how a system is evolving, and this is. I mean, two trajectories. So this is we are considering as initial condition, and they are very closely separated. Now, I mean, so what we want to know? So we want to know how Z evolves. So we want to know how ZT evolves as a function of time. So now, so we want to know how this is evolving. Okay. So from the equation, so this is our given equation. So from this, we can write x t. So this is our initial state vector at time t. So this will satisfy this equation. So we can write xt as function of x at time t, and we can also for the I mean other point we can write x dot t plus z dot t, which will be equal to function of, and here we will have x of t plus z of t. So this is how our I mean this is the governing rule for our two initially separated close by point. So I mean let us recall. So this is I mean uh, I mean so this is quite similar look like Taylor series expansion. So let us recall what is the Taylor series expansion in for in a 1D system, and then we try to I mean uh, expand this Taylor expansion to multi-dimension system. So Taylor series expansion for 1D system. So I mean you have one variable here. So I mean in state vector you have only x1. So x2, xn. So it doesn't exist. So you have only one state vector. Okay. So what is our Taylor series expansion formula gives? So it tells that f of x plus h. So that should be f of x. So I mean we are expanding this around x. So we have here x plus h square by 2 factorial f double prime x. Then we will have another term. Then we will have term n minus 1 into the power. Here we will have n minus 1 factorial f n minus 1 x, and then we will have nth order term, and so on. So I mean if I mean so let us say I mean if the function is continuous and if it is n times differential in the in interval, so the last term would be like this. So h to the power n by n factorial f of n x plus lambda h. So this lambda is from 0 to 1, and this is the case if f is continuous and n times differentiable. So now, I mean, if we consider the f to be analytic and I mean differentiable up to all the orders, so I mean, so then we can write I mean, so mainly we don't need to worry about that. So the I mean, so for initial understandings, we can assume that this f is analytic and all order differentiable. Then, if it is the case, so f is analytic, f analytic and all order derivative is exists, then the following condition holds. So what will be the condition? So limit n to the 10 to the power infinity. So h to the power n by n factorial function which will be nth order differentiable, and that will be 0. So now and that is 0 for n tends to infinity. So that means it is not diverging. So our series expansion will converge. So we are assuming that. So then we can, from Taylor series expansion, we can write this, that f of x plus h, which will be equal to, so j from 0 to infinity, h to the power j by j factorial f j x. So j is the order of derivative. So first it will be 0. So 0 the order derivative. Then we will have 1, 2, 3, and so on. So this is this is the Taylor series expansion of the function f of x around this point. So now, so what you can write? So from this you can write the Maclaurin series. So which is f of x, which is basically from j0 to infinity, and this x will be x to the power j by j factorial f of j0. So this can be write down as f of x equal to f of 0 plus x f prime 0 plus x square by 2 factorial f double prime 0 plus x to the power n by n factorial f n 0 and more terms. So this is the Taylor series expansion of f of x. Now, in the similar spirit, we can write the Taylor series expansion of a multivariable system. So when you are dealing with higher order phase space, so we have then we are dealing with a multi-order system. So if you want to expand this point, so this this point, so this is in a multi-dimensional phase space. So you have to know how what will be the Taylor series expansion of a multivariable. So let me generalize it. So this is for a system with one variable. So Taylor. So suppose instead of x only, we have this x, y, and z. So this is our function, and we want to expand it around x0, y0, and z0. So our function has now three variable, and we are expanding it around this x0, y0, z0. So from Taylor series up to the first order approximation, so what we can write? So we can write as f of x, y, z as f of x0, y0, z0 plus x minus x0 del f del x x0, y0, z0. Then we have y minus y0 del f del y, and f is a function of x0, y0, z0, and similarly we will have the last term which is z minus z0, and here we will have del f del z, and this f is a function of x0, y0, z0. And if we want to do it for second order, so up to second order, so second order is not important, but when not needed for Taylor series, but let me just show you once. So up to second order, how it will look like. So we have the function which is f x y z. So if we want to expand it, so we will have x0, y0, z0. Then we have here x minus x0 del f del x. So let me take the f out, del x plus y minus y0 del y plus z minus z0 del z. And here we will have f x0, y0, z0. So this is term of the first order. Then the second order terms will be half x minus x0 squared del 2 del x squared. Then we have y minus y0 squared del 2 del y squared. Then we have z minus z0 squared del 2 del z squared. And we have cross terms x minus x0 y minus y0, so del 2 del x del y. Then we will have other cross term also z. Okay, so I mean we will have the reciprocal term also, y minus y0 x minus x0 to del 2 del y del x. So similarly we will have x minus x0 z minus z0 will be del 2 del x del z plus z minus z0 x minus x0 del 2 del z del x, and other term which will contain y minus y0 z minus z0, and here we will have del 2 del y del z plus z minus z0 y minus y0 del 2 del z del y. So this is the expansion, and here you have your function alpha x y z. Okay, so it will be x0 y0 z0. So how we are getting this? So I mean, so you can do this from this. So the okay. So now this del 2 del x del y, you can write this as del 2 del y del x, and similarly for z y also. So I mean, if we write a as x minus x0 del x, b as y minus y0 del y, and c as z minus z0 del z. And if we want to compute what is this a plus b plus c square is, so in that case what we will end up with is 2ab 2bc 2ca. So this term that we are getting here, so it is basically squared. So if I put this a b c and do this, so effectively we will end up that this is equal to the equal term that we are getting here. So we can write the function now as, so this function x y z, that can be written as function at x0 y0 z0. Then we have here x minus x0 del x, y minus y0 del y, Z. Okay, then we will have Z minus Z0 delta Z, and here we will have function at x0, y0, z0, and then we will have this function which is 1 by 2 factorial x minus x0 del del x, y minus y0 del del y, and z minus z0 del del z squared of this, and here we have f of x0, y0, z0, and we have other terms. So this is how the Taylor series expansion up to second order will look like for a multivariable system. So I mean, if we have more number of, so if we have an n variable system, so let me write down that. So what will be the general form? So this f x1, x2, and this will go up to xn. So this we can write as function at x10, x20 up to xn0. Then we will have here xj minus xj0. So because we are seeing here x minus x0, y minus y0, z minus z0. So this is xj minus xj0, and here we have del del xj, and this j is going from 1 to n, and here okay, so this will be under summation, and here we will have x10, 20, n0, and here we will have the higher second order term which is j1 to m, here we will have xj minus xj0 del del xj, and squared of this, and we will have x10, x20, xn0. Okay, so this is the Taylor series expansion for a system with n variable. So effectively we can, I mean, write down as f x1, x2, xm. This is from k equal to 0 to infinity 1 by k factorial, j equal to 1 to m. Here we have xj minus xj0, and we have del del xj, and this term here the power. So power also, I mean, depends on what k is. So it is k, and function is f capital. So this capital F evaluated at x 10, 20, m0. So this is the rule. I mean, this is the Taylor series expansion rule of n variable system, and so f is the governing update rule, and so I mean, so this is how, I mean, if you have any function which is a, you have any form which is a function of this variable, and I mean you know what is the value at a certain point, then you can calculate, I mean, value at another point which is this one using this formula. So this is the, I mean, extension of Taylor formula for multivariable system, and so now let us use that. So suppose this x j prime, this is governed by this rule. So gj x1, x2, x3 up to xm, and we have suppose we have another close by point which is x j prime plus x h prime. So let us recall why we are using it. So look at this. So these are governing equation. So we are taking two very close by separated point. One is xt and another one is xt plus zt. So they follows this update rule. This both of these points. So and how this we can expand f of xt plus zt, that we have learned from this. So this Taylor series expansion formula. So let us try to use all of them. So we have this xj and it's updating with this g, and we have another close by point. So how we will write this? So it will effectively be this gj, and x1 will be, so x1 plus h1, and this will be x2 plus h2, this will be x3 plus h3, and the last term will be xm plus h. So this is, so for example x for consider j equal to 1. So you are looking at the evolution of x1. So for example, if you have a harmonic oscillator, so x1 can be your displacement, and so this is how your displacement is changing, and here you can have function which depend on position, which depend on displacement, velocity. Suppose you have multiple oscillators coupled, so you have 10 oscillators coupled. So this xj, so for example you want to know what is the displacement of first oscillator, so this will be your j equal to 1, and here you will have these two will be for first oscillator, and maybe x3 x4 is displacement and position for second oscillator, x5 x and x6 is displacement and position, displacement and velocity for third oscillator, and so on. So the idea is that here you are looking at the evolution of each parameter, so each state variable and each state variable. So they depend on other state variables also. So as we have seen in case of harmonic oscillator problem. So don't be confused with that. So we have two these two closely separated points, and we can write this update tool. So now using the Taylor series expansions, we can expand this. So let me show you what it will be. So this xj prime plus hj prime, this will be gj. This will be equal to this. So this we can write as by using the Taylor series formula. So this we can write as summation from k 0 to infinity 1 by k factorial, and here we will have, so so since j is already here, so we will change the notation. So here we will introduce another notation, because we are summing over it. So the notation ultimately it will be summed up. So since we are already considering j here, so so that you don't so to avoid confusion, so let me write it I. So I will run from 1 to m, and here we will have hi, which is basically the separation. So hi is basically separation between xi and xj0, and we have here xi and to the power k, and here we will have gj, and it is x1 x2 will go up to xm. So this is the update rule for x plus xi plus hi. So this is our xj dot, and this is our xj dot plus hj dot. So what is hj dot? So hj dot is basically evolution uh, along each state variable direction. So if you have a harmonic oscillator, so you have h1 and h2, and h1 is the evolution along, it is the axis along displacement, and h2 is along the velocity. So h is basically the evolution. So each and this you can compute. So you can, I mean, from this two you can easily look at what it will be. So it will basically gives you. So first you will put k equal to 0. If we put k equal to 0, this will be 1, this will be 1. So effectively this and this term will cancel out. So for h dot prime, it will simply be from k1 to infinity 1 by k factorial, and here we have summation I from 1 to m h I del del x I to the power k g j x1 x2 xm. So now, I mean, if this x10, so this is how the how the difference between two closely separated points are evolving. Now suppose suppose there is an equilibrium point, which is, I mean, x10, x20, xm0. This is our equilibrium point, and we are considering all edges to be infinitesimally small. So initially they are very small. So initially when you are considering two close by separated trajectories, so in that case each of the edges that has to be infinitesimally small. So initial values infinitesimal. So if that is the case, then we can, I mean, neglect the higher order term, and we can write xj prime xj dot to be from I. So we can only consider the first order term, and we will write here xi del del xi, and here we will have gj x1 x2 up to xm. So this is how the I mean xj prime will evolve. So this we can write as I from 1 to m del gj del xi and hi, and this is our hj. So this is the, I mean, how the separation evolves in each of the state vector. So let us consider a case. So suppose we have for m3. So in that case, how what will be the equations look like? So j will run from 1 to 3. So first let us take j to be 1. So h1 prime, which is, so first I will be 1. So it will be gj1 del x h1. Then we have gj1, because j is 1 for the first equation, and then we have to summation over I. So del x2 h2 del g1 del x3 h3. So this is how x1 will evolve. Then we have x2, which it will be, so now j is 2, so we have here 2. So del x1 h1. Then we have del g2 del x2 h2. We have del g2 del x3 h3, and similarly we will have the last term, which will be h3 prime equal to del g3 x1 h1 del g3 x2 h2. Then we have del g3 x3 h3. So this is how, I mean, each of the equation will evolve. So this is for a three-dimensional system. So I mean, what are these g's? So g, I mean, so I mean, if we have a harmonic oscillator, then we they are m equal to 2. So let us consider the case d2x dt square equal to minus omega square x. So you can write this as dx dt equal to phi and dv dt equal to minus omega square x. So your x1 is basically x, x2 is basically phi, and your g1 is phi, g2 is minus omega square x. So this functional form, so they are these are your this g functions. So and what are the and what is h1? So h1 is basically how the separation is evolving along this direction, and h2 is basically how the separation is evolving along this direction. So how separation, and this h2 is how separation, I mean, so dot of this. So their variation tells you how separation is evolving. So separation is evolving along v direction. And so you are done with G1, G2, and H1, H2 is how your separation is evolving. So by using this equation, you will find how H1 and H2 is evolving. So generally, what you can write? So you can write so Hj prime is equal to, I mean, so it is at this. So I equal to 1 to m del g j del xi h I. But I mean, we can, okay, so this we can consider it. So since it is summing over I, so we can call it Hj. So Hi prime, so Hj prime, we can call this as Aj Hi. So and what is this Aj? Aj is basically this I equal to 1 to m del Gj del Xi. So this, I mean, in matrix form. So you can write this as H prime H dot, which will be equal to A into H. So here this A is generally known as Jacobian matrix. Okay, so here you can see, I mean, how the Jacobian matrix naturally comes from, I mean, from the basic theory of Taylor expansion. So we have started from the scratch. So we have, I mean, taken two initially separated condition. Then we have, I mean, implemented this Taylor series expansion multidimensional, and from that we are looking at how this H is evolving. So the separation between two closely separated trajectories. So how that is changing. So now from that we are getting this condition. Okay, so now we'll take take a quick 2-3 minutes break, and then after that I will proceed, and I will show you how you can get the, ultimately you can calculate what is the uh, Lyapunov exponent of this system. Okay, so what we have learned? So we have learned that if we have a system who is I mean who is which is governed by this equation, so x prime is equal to f of x, and also so we consider a close by separated point, and this equation look like this. And what is this x? X is a so x is a state vector which is x1, x2 up to xm. Then you have this h vector which is h1, h2, hm. So transpose of it. So and we have this x. So what is this xj? So I mean if I write down the so from this we can write hj dot equal to I1 to m del fj del xi hi, and this can be written as h dot can be written as a into h, where a is the Jacobian matrix. So effectively a looks like in this way. So a is del f1 del x1 del f1 del x2 del f1 del x, so it will go up to xm. Then we have here del f2 del x1 del f2 del x2, it will go up to del x del f2 del xm, and there will be last term will be del fm del x1. Here we will have del fm del x2, and this term will be del fm del xm. So this is how your A matrix will look like, and so this is how the separation between closely two separated points in phase space will evolve. So this is the rule which the infinitesimal difference between two initially separated trajectories are evolving. So this is the rule according to which infinitesimal infinitesimally closed by separated trajectories in phase space will evolve. So I mean this A matrix will be different according to the system. So I mean for different system you will have different functions, and from that function you can calculate what is the A matrix. So and you can subsequently you can find what is the rule according to which the system is evolving. So I mean to know how the difference grows with time, so you can write down the first order differential equation of all the independent variables and compute the, so what you have to do, so you have to compute the Jacobian of the function of each variable. So uh, I mean if you I mean don't remember what is this, so just follow what I am. So I mean if you don't have to remember all of this. So what you have to do, so practically I mean you have your differential equation. So I mean write down this in first order differential equation. So I mean if you have nth order differential equation, so you will have n first order differential equation. So write down the functions, compute the Jacobian. So you will get how up the update rule. Now, from this update rule, we have to know how. So let us proceed further with this update rule. So we in this way we can gain the we can get the evolution rule for the separation, and that I mean and that will be different for different systems. So now, since this h prime is, I mean, h dot is equal to ah, so we can write, h at t plus delta t, which will be equal to h at t plus a h. So we are using the Euler method. So let us just use the Euler method now. So a h t delta t. So we know that h prime equal to h t plus delta t minus h t divided by delta t. So this is how your h prime will change. So if you put it in equation, so you will get this, and from here you can write h at t plus delta t, which will be equal to identity matrix plus delta t multiply with a, and you will have h here. So this is the rule that governs the evolution of the infinitesimally separation between 2 points in the phase space from t to t plus delta t. So this is evolution in one space. So now how you will compute this in numerically. So let us look at the how you will do this numerically. So suppose this is your initial time and this is your final time. So now suppose this is t1 and this is t1 plus delta t. So what you can do, we can assume delta t to be uniform. So the point this we can assume to be uniformly separated. So now what this point will be? So it will be t1 plus 2 delta t. This will be t1 plus 3 delta t. This will be t1 plus 4 delta t. So this is how time is evolving. So we can write h at t1 plus delta t will be equal to identity plus delta t into a at t equal to t1. So a at t equal to t1. Then we will have here h t1. Similarly, we can write h at t1 plus 2 delta t. So that will be equal to I plus delta t, and here we will have a at t equal to t1 plus delta t, h t1 plus delta t, or and now this h t1 plus delta t, so we can put this value. So in the previous step we have computed it, so we can write I plus delta t, and we will have a at t1 plus delta t. Then this is I plus delta t into a1 at t1, and here we will have h at t1. So similarly, if we compute what is h at t1 plus 3 delta t, so let me compute another one. So it will be I plus delta t a at t equal to t. So the previous time was t1 plus delta t. So this will be at t equal to t1 plus 2 delta t. And here you will have h at t1 plus 2 delta t, and this you can substitute from your previous step. So effectively this will look like I plus delta t into a at t1 plus 2 delta t. Then you will have I plus delta t multiplied with a at t1 plus delta t, and you will have also I plus delta t multiplied with a at t1, and you will have h at t1. So t1 is your initial point, and if you know what your initial time is, so then and if you know what your Jacobian is, so you can compute the Jacobian at each of the time step, and you can keep on repeating this multiplication, and you will get what is the age value after certain time step. So in general we can write. So what will be the general form? So general form is h at t2. So t2 is the final time. will be multiplication. So here we have multiplication of I, and we will have I plus delta t, and here a at, so I mean xi, and these xi's are evaluated at ti, and here we'll have h at t1. So in discrete time we can write this, I mean if we want to write it in terms of step, then we can write this at hn plus p will be equal to from I0 to p minus 1 I plus delta t a at x n plus I h h n. So I mean, so why I am writing n here? So n we can take 0, but I mean whenever you are working with the system, so initially there can be some transient. So you will exclude some initial point. Suppose you are simulating a harmonic oscillator equation. So and you have 10,000 point in your time array. So you will, I mean, so if maybe you want to exclude the first 1,000 point, and after that you want to have the initially separated point. So n you can put 1,000. So I mean you're starting from 1,001 data point. So that will be your initial separation you can compute. So I mean you can just compute the difference between two matrices. So that will be your h, and I mean you can compute what is a at each time step, and you can multiply it with gt. So you have to, I mean, keep on repeating the task. So I mean, so and it will go from p minus 1. So p is, I mean, basically length of p. So this is the total length, and from that, yeah, I mean, you are also excluding this n number of data points. So p should be this length of t minus n. So to evaluate this h n plus p, I mean, or the, so what is this h n plus p? So it is basically the distance at a very large time. So let me write it here. Very large time compared to the characteristic time scale of the system dynamics. So what does that mean? So I mean in your system you want to, I mean you will have an idea what is the maximum time scale present in your system. So for example your system has lowest frequency 1 hertz. So the maximum time scale in your system is 1 second. So now you want to simulate the system up to a time which is larger than 1 second. I mean, so maybe you can take up, you can simulate the system up to 100 second, and this h n plus p is the separation after the 100 second. So that is, I mean, very large compared to the characteristics time scale of the system dynamics. So as I'm mentioning, so what is the process? So first remove some transient data, then assume, I mean, so I mean assume a very small separation apart between, I mean consider two initially, I mean two very separated close by separated point. Then we have to compute this Jacobian at each of the time step. So I mean when for this time array, so I mean 0 dt, so t final. So I mean, so this t, okay. So it's starting from 0. So what you will do? So you will initially remove some transient. So suppose after transient your time is ti. So from in this range, from ti to tf, you will compute your Jacobian at each of the time step, and you keep on repeating the same task. So you will end up with what is h n plus p. So I mean, so formally we can write that h n plus p is I0 to p minus 1 I plus dt I Then we have here a x n plus I h n. So this is the formal update rule. So update rule. So I mean you have to write a code in MATLAB corresponding to this. So I mean if we call, so let us assume this whole thing, I mean this uh, without this hn. So this thing let us call it to be zp. So so now in short we can write hn plus p equal to zp hn, and just drop down the n now. So hp is basically zp h0. So this is how I mean this is your separation between two close by separated point initially, and this is after p steps. So now I mean, so if this has eigenvalue, so I mean, so this is a matrix, so it will have some eigenvalue. So I mean, if the eigenvalue is lambda, then we can write as, so this equation we can write as alpha I h alpha j h0 j. So what is this alpha j? So it is the eigenvalue. So how many eigenvalues will be there? So their eigenvalues will be equal to the length of the state vector. So the number of eigenvalues, state vector. So from this we can write down this. Now suppose we are assuming that this h or this delta pj, so I mean, or let me write down this, let me not introduce any more variable. So hpj, so suppose we are writing this as h0j into e to the power uh, p lambda j. So I mean we are assuming that this h0 along z, so h or the separation along z axis, phase axis, so that is exponentially changing. So I mean, so now this delta j, so this I mean this will exist for all of the state vectors, and how we can compute this? So this is also, so this hpj is also equal to alpha j h0j. So from that we can write that alpha j will be equal to e to the power p lambda j. So lambda j, from this equation we can write down as 1 by p ln alpha j. So this lambda, so they are known as the Lyapunov exponent. So how many lambda j's are there? So basically, so it is equal to the number of j's, and j is runs from, so it runs from 1 to length of x. So that means, uh, so it depends on how many state vector you have in a system. So in a harmonic oscillator system, you have state vector to be x, b. So j will run from 1 to 2. So you will have two Lyapunov exponent. So for harmonic oscillator, if harmonic oscillator, so if there is no independent time axis, so in that case you have two Lyapunov exponent. So I mean, and if you have coupled harmonic oscillator system, so if you have two oscillators which are coupled, then you need position of both the oscillators and velocity of both the oscillators to specify the state of the whole system. So in that case, you have four Lyapunov exponent. and I mean each of the Lyapunov exponent you can calculate from, I mean, if you first you have to calculate what this alpha j are, and what this alpha j are. So they are basically the eigenvalue of this A matrix or this ZP matrix. So ZP, so the process is that first you have to write down what is the Jacobian for a system, then you have to evaluate the Jacobian at each time step, and you have to keep on repeating this task and do this multiplication. So so you will first you will remove some transient data, and after that transient data, for the whole sequence you will ultimately get this number. You will ultimately get an matrix from it, and from that matrix you have to compute, you have to get what is the Lyapunov exponent of the or what is the eigenvalue of the matrix, and these eigenvalues are related to the Lyapunov exponent through this relation. So from that you can calculate what are the Lyapunov exponent corresponding to it. And you can also, I mean, so as we have stated that if lambda is greater than 0, so that means, I mean, if you look from here, so p is always 0. So if lambda is greater than 0, then what is happening? Then, I mean, yes, this separation is diverging. So that we can tell easily from here. So that is why lambda greater than 0, it basically implies that if your system has chaos or not. So condition. So what is the condition? So at least one lambda j, that should be greater than 0. And also, I mean, if you have a system where two lambda j's are greater than 0, so that basically leads to hyperchaos. But I mean, we will not go into too much details of that. But if you want to have system, if you want to check if in your system there exists chaos, so this is the step which you have to follow. So you have to, I mean, so this is the, I mean, process to compute this Lyapunov exponent from model. So we know what the model is, and from the model, I mean, we can compute what is the Jacobian for this model. Then we can evaluate the what is the value of the Jacobian matrix at each of the time step. Then we will keep on repeating doing this task. Ultimately, we will get the matrix, and from the matrix we can calculate what is the eigenvalues. And if any of the eigenvalues, so then we have to apply a condition statement that if any of the eigenvalues are greater than 0, so that basically leads to chaos. So let me show you just okay, so you can try to implement so this code in MATLAB, but let me just show you one example how you can compute the Jacobian. So let us consider a slightly complicated system. So we have, let us consider example, two harmonic oscillators coupled. So suppose we want to uh, let us so write down the model equation. So for example, so for let us write down equation 1, which is x11 x double prime gamma x prime, then we have omega square, and suppose here we have it I mean forcing term. So force cos omega ft, then we have x, and we have beta x cube, and suppose we have another term eta x square x dot. So this is, I mean, known as non-linear damping or van der Pol oscillator. So it is included. So suppose in a system we have this, then we have alpha. So also let us consider a coupling. So alpha x1 x2 alpha xy. So this is your oscillator. This is the equation of one harmonic of one oscillator, and suppose we have another oscillator. So x double. So let us write this to be y. y double prime, and we have gamma y prime. Then we have, so let me call it gamma 1 omega 1. It is gamma 2 omega 2. So this will be omega 2 square y, and suppose here we have this direct drive, so f cosine of omega ft, and we have alpha prime xy. So let us take this two equations. So I can see that these are coupled. So this is, I mean, two oscillators which are linearly, which are coupled to each other. Now you want to check. I mean, you now suppose you want to check what is the, I mean, how you can, if there is any chaos for the system. So suppose you are driving the system and you are increasing the driving strength. So in the last lecture we have discussed how you can do that. So you have to create a loop for f. So I mean, with that loop you are suppose driving the system with in increasing f, and with increasing f you want to know if there is chaos in a system. So what you will do, so first you will run the system for one particular f. So for example the f, so suppose f is array which is running from 0 to 10. So first you will take f value to be 0, then you will solve, then from this equation you will write down the Jacobian, then compute the Jacobian for the range of time length, I mean for each time step. Then you will compute what is the, you keep on multiplying the, you keep on multiplying those terms, so you will end up getting the final matrix, and the final matrix you calculate what is the uh, lambda value. So and then you keep on repeating this process for different f. So for f equal to 0, then for f equal to 1, for f equal to 2, and so on. So in that way you will get what is the lambda, what is the Lyapunov exponent for each of the value, for each of the direction. So then I mean, so if you want to know if there is any lambda which is greater than 0, so then you can look for only the maximum of the lambda. So because you, for chaos you have to have only one lambda which is greater than 0. So by looking at the maximum is sufficient. So that is why you can look at the maximum of the lambda with increasing it. So I mean, you can try to look for, so this is suppose your f, and this is your maximum of lambda, and for each f you compute lambda. So suppose this is the 0 uh, or scale. So this is where y is I mean 0. Suppose for f equal to 0 and this is f equal to 10. Suppose. So for f equal to 0, maybe your maximum lambda is here. I mean, maybe it is minus 2, this is minus 1, this is 1. So I mean, maybe your system is starting from here. Then I mean, with increasing f, maybe you will see that how your, I mean, so and there will be a certain point after which it will go to 0. Then I mean, it may perform some fluctuation around this point, and after that it is eventually going to, I mean, it is greater than 0. So you can see, so from by looking at this lambda curve you can tell when your system is behaving, I mean it is in the chaotic regime and when it is non-chaotic region. So for this range, so this is the, I mean, range where the system is non-chaotic. Then in this intermediate range it is in the chaotic regime. Then here for small window also this is in chaotic regime, and after that it is, the system is again in the chaotic regime. So by looking at the, I mean, this Lyapunov exponent, you can tell a lot of information about system. So I mean, uh, so you know that if your system is in this range, so I mean if this is your drive strength, then this your system is chaotic. So then you cannot infer about what I mean you cannot predict the state of the system, because in that case two very closely separated trajectories will diverge. So let me show you first the process of computing Jacobian. So I mean, we can from this two equation we can write that x1. So let me call this x dot and y dot. And so I mean, in nonlinear dynamics, basically when you have an explicit t present in the system, so you consider that also to be a state vector. So this is your state vector representation. So let me rename this as x1, x2, x3, x4 and x5. So this is your state vector. So from this, what will be the equation that you will get? So your x1 dot will be x2 and this is your f1. Then you will have x2 dot which is minus gamma x2 minus eta x1 square x2 minus beta x1 cube minus omega 1 square, and this will be gamma 1, and here you have plus f cosine of omega f, and t is our x5, so x5 x1, and we have alpha x1, and what is y3? Y is our x3, so this is x3. And similarly we will have x3 dot which will be x4, so this one is our f2, this is our f3, and then we have x4 dot which is basically minus gamma x4, so gamma 2 minus omega 2 square x3. Then we have alpha prime x1 x3, and there will be another term which is f cosine omega f x5. So this term is your x4, and you will have t dot. So basically x5 dot is basically your t derivative of t with respect to t, which is 1. So this is your f5. So you have gotten all the function. So now how can you write down the Jacobian? So for Jacobian, okay, so let me write it here. So this will be your Jacobian matrix. So what is the process? So here you have to compute del. So let me go back. So you have to compute this del f1, del x1, del f1, del x2 and so on. So f1 is your x2. So first term will be 0. So okay, let me divide this first. This will be, okay, we will see. Second term will be 1, third will be 0, fourth will be 0, fifth will be 0. Now let us look at the second f2. So del f2, del x1. So these are f2. So if I take partial derivative with x1, so this term will give me 0. So there will be this gamma term will present. So it will be minus 2 gamma x1 x2. There will be minus 3 beta x1 squared, and also we will have this minus omega 1 squared plus f cosine of omega 5 omega f x5, and we will also have this alpha x3. Okay, so this is our del f2 del x1. What is del f2 del x2? So so it will be minus gamma 1 minus eta x1 squared, and there is no x2 term, so there will be no more element. And x3, so we will have this alpha x1. So if I take partial derivative of this term with respect to x3, so there is only one term, so this will exist here, and there is no x4, so it will be 0, and in x5 we will have minus f, and cosine derivative is basically sine, so minus will cancel out, so sine omega f x5, we have x1 and omega f. So be careful with this derivative. So but this is how it actually it proceeds. So del f2 del x. Now we have to check for the f3, and f3 is quite simple. x4. So basically all first three terms will be 0, fourth one will be 1, fifth will be 0. Then we have x4. So is there any x1 term? So yeah, so alpha here we will have alpha x alpha prime x1. And is there any x2 term? No, so the second term will be 0. And is there any x3? Yeah, so here we will have minus omega 2 square, and here we will have alpha x1 alpha prime. And is there any x4 term? Yes, so gamma 2 will be here, and x5. So yeah, here we have x5. So yeah. So if I take derivative with respect to 5, so this will give me minus f omega f sine omega f x5. So I mean you can check if it is right or wrong. So I'm just doing it right now. Okay, so this is del f4 del x5. Now you have to look at your x5, which is 1. So if you do this, so it will give you 0. Fine. So this is your Jacobian. So now I mean this variable you will define initially. So you will have you will have a set of parameter values, and then in each time step, so with this RK4 method you can compute what are this x1 x3, this x vector you will compute at each time step. So you will put this into this Jacobian matrix. So you will evaluate the Jacobian at each time step, and you key, and if you can compute what the Jacobian is, then you have to multiply that with delta t, and you have to add an identical vector with it, and you have to keep on doing the same task in for the rest of the time steps, and you just keep on multiplying it. So you have to do the same task repeatedly. So you just tell the computer to do that, and ultimately you will have the final matrix. This is Z matrix. Then what you have to do, you have to check its eigenvalue, and that is quite simple in MATLAB. You have to write this eigen command that will give you the eigenvalues. Then look for the maximum of the eigenvalues. So you know how to sort the maximum element from an array. So and just repeat the process for different types. So you will have an array of derived strength, and also an array where you will store the maximum value of this eigenvalues, maximum of the eigenvalues. So then you can plot, and you can you can check if so maybe you will have some graph like this. So if there exists chaos for the system, or if there is no chaos, so you will end up with maximum eigenvalue less than 0. So that, so in that case you can say that okay, in my system, in the for this parameter range, so there is no chaos, so it is periodic, or it is converging, or the system is stable. So you can check for other parameter values and so on. So this is the way in which you can take any kind of complex model, and you can look, you can check for if there is any chaos in the system. So the power of this method is that if you know what the model equation is, then you don't have to worry about the dimension of the system. So you can take so what you need to worry about is the computational power. So you just have to tell the computer that this is my Jacobian. Then they so yeah, and you have to compute this Jacobian by hand. That also you can do by mathematics also. So so in this way you can take any complex any complex any complex kind of model, and you can try, and if you can search or hunt for, you can look, try to look if there exists some kind of this unpredictability behavior in the system for a certain range of parameter values. So first you can, so for example you want to check for different beta values. So you check for initially for beta 0, so there you are not observing any chaos. Now you can change the beta. So yeah, you can increase the nonlinearity, and you can look for chaos. And if there is not chaos, you can again change the nonlinearity and so on. So the key, the so that is the key takeaway of this thing. So I will not write the code for this. So and this is pretty much everything which we have done earlier. So solving a differential equation, solving. We have solved also the projectile motion problem where we have four first order differential equation coupled. So you can proceed with that example also. So if you think this is complicated, so proceed with that, because in that case there is no chaos. So you can verify that you verify that there is no chaos. You show that this lambda is less than 0. So by that way you will get some confidence, and then you can you can take on more complex models, and you can work with that. Okay, so I guess that is it for today's lecture. So in the last lecture, in the next day, so I will I will briefly introduce you to the concept of this stochastic oscillator system. So it's a vast topic itself, and it will take a whole semester to it's itself is a topic of research, but I will just briefly introduce you to the very basic thing. So the modify what modification you need to do in your numerical method to do this stochastic kind of to do simulation for the stochastic kind of systems. And we will do some basic examples, very basics, and after that we will wrap up the course. Okay, so that is it for today's lecture, and I will upload all of this in the drive, and I will share the link. Okay, so yeah, so see you in the next lecture.